Hey everyone. Before we dive headfirst into Season 2, it's really worth making one short stop. You see, in Season 1, we packed our entire toolbox for the frame budget approach. But before we turn that toolbox loose on big topics like quantum measurement or cosmology, we really need to talk about a few words that we all tend to use way too casually. Words like randomness, development, and path. Okay, let's get into it. So yeah, a very warm welcome to this little SciencePunk Intermezzo. We're doing this because we're about to go after some of the biggest questions in physics. And to do that, our language has to be just as precise as our thinking. So this short explainer is really all about sharpening our concepts. So let's quickly jog our memory. Remember this from Season 1? This is our conceptual toolbox. We learned to think in terms of frames and minimal events. We learned how to define a system with an accounting boundary. We tracked all the action using a budget and a channel. We carefully separated out reversible and irreversible contributions. And maybe most importantly, we started to see measurement not as a passive look, but as a real physical coupling. These are the tools we'll be working with.
Okay, here's our game plan for today. We'll start with why we're taking this little stop in the first place. Then we'll revisit the FBA's core idea of how development actually happens, step by step. From there, we're going to challenge that everyday notion of randomness, and that's going to lead us to some much sharper language, path bundles. Finally, we'll see how all this gives us a really powerful way to think about why it's so much harder to go backwards than forwards, what we're calling the asymmetry of return.
So as we're gearing up for Season 2, we're getting ready to apply the frame budget approach to some seriously big ideas. But to do it right, we first have to take a closer look at some words we use all the time without even thinking about it. Words like randomness, or even development. The FBA demands a kind of precision that just forces us to re-examine them. So let's start with the most basic thing of all, change itself. How does anything happen? Well, the FBA's core idea here is actually pretty radical. It says that development isn't some smooth, continuous flow. It happens in discrete, countable steps. And this, right here, is the absolute DNA of the frame budget approach. Time isn't some river we're all floating down. It is the sequence of clicks of these discrete changes in state. Each frame is like a snapshot, an accessible slice of what's going on, and a minimal event is the smallest possible change, just one step, one click, that gets us from one frame to the very next. Honestly, this step-by-step view of reality is the key to everything that follows. Okay, so holding that step-by-step picture in your mind, let's tackle a big one, randomness. You know, we see a die roll, or we watch a particle decay, and we say, well, that was random. But what are we really saying when we say that? Is randomness some fundamental property that's baked into the fabric of the universe, or is it something else? So the FBA proposes this really fascinating shift in perspective. What if randomness isn't a property of the universe at all, but instead it's just a label for our own incomplete knowledge? What if it's just a placeholder we use for things we can't see, like missing resolution or hidden connections, or maybe just a past that's getting harder and harder to piece back together? In this view, randomness describes the limits of our description, not nature itself. So the crucial point is this. The FBA really encourages us to just pause before we jump to the word random. Instead, it asks us to use a much more precise vocabulary, to talk about what possible next steps or continuations a system actually has, to ask how those different options are weighted. Are they all equally likely or equally robust? And to think about what makes certain outcomes visible to us in the first place. Okay, so let's actually dive into this new language. If we're going to move away from a simple, kind of fuzzy idea like randomness, we're going to need better tools to describe how a system develops from one frame to the next. And this is exactly where the concepts of continuation options and path bundles come into play. So a continuation option is pretty simple, really. It's just a possible next step for a system, a physically permissible way for it to change from one frame to the next. But here's the really interesting part. Just because a step is permissible doesn't mean all options are created equal. Their visibility, their likelihood, all depends on our resolution, on the system's couplings, and on the specific conditions of the setup. And this illustrates the next crucial distinction. A path can be possible, but is it plausible? Is it robust? That's the key. We can't just count the number of possible outcomes. As it says here, admissibility is not robustness. A path might be technically possible, but incredibly fragile, requiring some kind of perfect fine-tuning to ever happen. But another path might be supported by a huge number of slightly different microscopic processes. And this leads us directly to the central concept here,
A path bundle. Think of it this way. A probable, stable, reproducible outcome, like a ball settling at the bottom of a bowl, isn't the result of one single perfect trajectory. No, it's the result of a whole family, a whole bundle of slightly different microscopic histories that all lead to the same big picture result. The outcome is robust precisely because so many paths lead there.
So, why does this matter? How does this new language of path bundles actually help us? Well, it allows us to tackle one of the deepest questions in all of physics: irreversibility. We all have this gut feeling that eggs don't unscramble, but why? Path bundles give us a powerful new way to understand this asymmetry. This simple diagram really captures the entire idea. The forward journey, from a highly specific state like an intact egg to a more generic, messy one like scrambled eggs, is supported by this massive bundle of possible microscopic paths. But what about the return journey? Well, the path back to exactly that specific original intact egg is incredibly thin. It's not necessarily impossible, but it's carried by a vanishingly small set of possible histories. The FBA gives this process a working name: path burial. And it's exactly what it sounds like. It's the idea that as a system develops, the number of compatible paths that could lead back to a very specific origin state just thins out. Information about that specific origin gets harder and harder to reconstruct. It gets buried under this ever-expanding set of forward possibilities. Now, this is absolutely critical, and the FBA is very disciplined here. Path burial is not being presented as some new ironclad law of nature. It doesn't claim that return is absolutely impossible. It's a carefully defined working concept to describe a real, measurable, observable phenomenon: this growing asymmetry of return and the declining ability we have to reconstruct a specific past. And one final crucial clarification: let's say, against all odds, a system does manage to return to a state that looks identical to a previous one. In the FBA, this is not time reversal. The sequence of frames is append only, it only moves forward. That return is a new event, a later realization in the sequence. It's not a jump back into an old frame. The clock, the frame index, always takes forward. So we're going to take 3 key things with us into Season 2. First, the FBA describes development as emerging from real discrete steps, not from some smooth background flow of time. Second, concepts like randomness or loss are often best understood as diagnostic words about our access, our resolution, and our ability to reconstruct the past. And third, with path bundles and path burial, irreversibility in the FBA gets a new and much sharper language. That is exactly the lens we are now taking into Season 2. This precise, operational way of thinking is what we're going to use to re-examine some of the deepest and most fascinating puzzles in all of physics. Bye for now, until the start of Season 2, and stay curious.